Okay, we're going to go ahead and get started. Thank you all for joining us. I am Perry Acree. I'm a visiting scientific specialist in emerging contaminants at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. As a land-grant institution, the University of Illinois at Urbana-Champaign has a responsibility to acknowledge the historical context in which it exists. In order to remind ourselves and our community, we begin this event with the following statement. We are currently on the lands of the Peoria, Kaskaskia, Piankashaw, Waya, Miami, Mascoutin, Odawa, Sauk, Meskwaki, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. It is necessary for us to acknowledge these Native nations and for us to work with them as we move forward as an institution. A few housekeeping items before we get started. Today's webinar is being recorded. The recording and slides will be available for viewing online in about a week. I'll be sending an email out to everyone who registered for the webinar once those are available. Everyone will remain muted for the entire webinar. You can type in your questions at any time through the Zoom Q&A feature. You will be able to upvote questions you like within Zoom Q&A using the thumbs up button under the question. I'll be reading the questions to the speaker at the end of the webinar. At that time, the most popular questions will be asked first, followed by questions in the order they were received. If you have any technical difficulties, please send me a private chat message. Also, if you need proof of attendance for continuing education credits or for any other reason, I will put my email address in the chat. So with that, I'm very pleased to welcome today's speaker, Dr. Meme Rahimi. Dr. Rahimi is an assistant professor of environmental engineering at the Cullen College of Engineering at the University of Houston, or UH. He also holds an affiliate appointment with the Material Science and Engineering program. Before joining UH, Dr. Rahimi was a postdoctoral associate at the Department of Chemical Engineering at the Massachusetts Institute of Technology, or MIT, from 2018 to 2021, working with Professor Alan Hatton. Dr. Rahimi obtained his PhD in chemical engineering from Penn State University in 2017 under the supervision of Professor Bruce Logan. His research group at UH develops electrochemical processes for climate change mitigation, including a wide range of technologies for carbon capture from air and point sources. Please refer to Dr. Rahimi's team website to explore more about the research activities, teamrahimi.com. The floor is yours, Dr. Rahimi.
Thank you so much, Perry, for the introduction, and it's a great pleasure to be here. Good afternoon, everyone. Today I'm going to talk about emerging electrochemical processes for climate change, specifically focusing on carbon capture and storage. So when it comes to climate change, the usual suspect is always carbon dioxide. And if we actually look at the historical emission of global CO2 for the past few decades, we see that there is a significant steady increase. And obviously, if we don't do anything, it would keep increasing. And this so far caused some serious problem, for example, increasing the global average temperature. So in order to have a sustainable future, we have to significantly reduce the carbon footprint or global CO2 emission. And experts design a portfolio to achieve this reduction that includes a diverse option. For example, going towards renewables, changing the fuel we're using, and also focusing on carbon capture and storage. But before talking about this strategy and specifically focusing on carbon capture, I want to spend a little bit of time focusing on the numbers we're talking about here. So here, for example, in 2060, we have to reduce our carbon footprint by 30 gigaton. But how big is 1 gigaton? In terms of the mass, if we combined the annual global production of all of these foods together, the annual global production, it would be only 1 gigaton. And these are the key components in our food. Potato, tomato, everything together, it would be, in terms of mass, it would be only 1 gigaton. And in terms of the volume, when we talk about 1 gigaton, it would be equal to the volume of a building if we built on top of the city of Houston, which is huge. And the height of that building would be 14 kilometers. And 14 kilometers, basically 30 times the height of the Willis Tower, which is the tallest in downtown Chicago. So when we talk about 30 gigaton of CO2 reduction, both in terms of mass and volume, we're talking about a significant number here. So any option, any strategy that could help us to reduce our carbon footprint would be beneficial. So there are some traditional roles for electrochemistry. The most that could help us reduce the carbon footprint. The most conventional one that you're all aware of is basically electrochemical energy storage, or for example, batteries, which could play a role in this green wedge of this portfolio, which is related to renewables. What they do is basically storing the solar and wind energy in order to have a sustainable, continuous source of energy. So eventually reducing the carbon footprint. The other more conventional electrochemical system is basically electrochemical CO2 conversion specifically to fuels, which can be a part of this orange wedge, changing the fuel, going towards a more sustainable fuel. The idea is we take CO2, we convert it to something that can be used as fuel in order to burn a fossil fuel. And when we look at these two areas, we see that just looking at the number of publications, we see that these two are pretty active in terms of research, and they have been around for some time. But there's also an emerging role for electrochemistry that is impacting the blue wedge, and that's basically developing electrochemical processes that could eventually impact the part of the portfolio that is related to carbon capture and storage. So the main theme of this presentation would be talking about different scenarios that we can basically develop an electrochemical process that could serve as a system for carbon capture and storage. So before talking about the system itself, I want to refresh your mind about the electrochemical reaction, which is basically the backbone of any electrochemical system. These are a chemical reaction, but in addition, we have this electron involved. So having this electron in our reaction would give us the ability to either apply electricity to drive this reaction forward, for example, when we're charging our cell phone battery, or to go backward and produce electrical current, for example, what is happening when we use our battery. So having this would give us a lot of ability to integrate renewables, to bring renewable electricity to play with this reaction. Going forward, reduction, going backward, oxidation. In short, we call this type of reaction a redox reaction. So the electrochemical system built upon this electrochemical reaction have some unique advantages. Obviously, they rely on renewables. They also very modular. Just in terms of the scale up, it would be a relatively straightforward task by putting individual units together because it's modular in nature. It is also easy to retrofit. That's one of the concerns, for example, when it comes to a point source carbon capture. We have a power plant that is producing tons of CO2, but if we want to integrate a carbon capture unit into that power plant, it would be a tricky job using the conventional method. But the unique aspect of electrochemical system is easy to retrofit relatively to the conventional methods. Also, it is a plug and play system. You plug it to electricity, and then you can run the system, you unplug it, you shut down the system. Again, it's relatively easier compared to the conventional technologies. So now the question would be how we can design an electrochemical system that could be an additional asset to what we already have for carbon capture. So this could be an additional asset next to absorption-based system, adsorption, or membrane-based systems. And the application would be the same as the other system do for carbon capture. It could be removing CO2 from air, point source, or mobile sources. And later on, that can be sent to either for storage or utilization. But the very first question when we want to develop an electrochemical system for carbon capture or for CO2 separation is that how we implement it. In order to answer this question, we categorize all of these electrochemical scenarios that could eventually separate CO2 from a gas mixture into 4 categories. So these categories are different in terms of their approach towards using this electrical current in order to eventually separate CO2 from a gas mixture. The very first one would be electrochemical generation of nucleophiles. So what is happening here is basically introducing the gas phase, which there's CO2 in it, some concentration of CO2, to a gas diffusion electrode in which the gas can be transported to the liquid phase. And on the cathode side, where the reduction is happening, we're reducing an organic molecule in which upon reduction, we're generating a nucleophilic site on that organic molecule. This nucleophilic site is attractive for carbon dioxide from its electrophilic carbon center. So as a result of this reduction, we can selectively remove CO2 from this gas mixture by forming this bond between the organic molecule and CO2. But this is half of the job. We capture CO2 from a gas mixture, but we have to also separate it and also regenerate the absorber. So what we do here is basically doing opposite. On the anode side, the oxidation of what was reduced, and upon the oxidation, we will release this CO2, regenerate this absorbent, and repeat the cycle. The regenerated CO2 will be transported by a gas diffusion electrode, and then it will be removed as a pure gas using a sweep gas. So this is basically how we use an electrochemical reaction, a redox reaction, through generation of nucleophilic site in order to selectively remove CO2. So that's one approach. The second family of electrochemical processes for CO2 separation is basically electrochemical modulation of proton concentration, or sometimes it is referred to as a pH swing process. In this case, we have the same gas diffusion electrode, but here, upon the reduction of this organic molecule, we don't form this nucleophilic site, rather we involve proton in this redox reaction. So we consume proton, it results in a local high pH, and as we know, based on the thermodynamic of CO2, when we have a local high pH, it can be absorbed as bicarbonate. And on the other side of the cell, by reversing the redox reaction, we generate proton, reduce the pH, and then regenerate this regenerate the molecule and remove the separated CO2. We're going to talk about the details in a bit, but this would be the whole approach and the difference between the second category and the first category. So the third category is basically using capacitors, which is a known electrochemical system, through an electrochemical capacitive adsorption. So here what happens is basically absorbing CO2 first as bicarbonate and proton, just a chemical absorption, and then sending it to an electrochemical cell that we do adsorption of these ions on the surface of the electrode. And that's how we remove this chemical species from the solution on the surface of the electrode through capacitive adsorption. The fourth category is basically electrochemically mediated amine regeneration. This is a bit more involved. This is inspired by a conventional amine-based thermal processes. And the idea is we oxidize or reduce a metal mediator in order to desorb what was absorbed in the absorption tower. So these two categories, we're going to talk about the details in a bit, and this is basically what we are developing in the lab. But before this, I'm gonna briefly talk about the molecules that are suitable for this approach and slightly talking about different manifestation of electrochemical capacitive adsorption. So first focusing on these two in a bit, and then the major part of the presentation, we're going to focus on these two techniques. So in terms of the electrochemical generation of nucleophiles, as you might guess, the core is that organic molecule we're using. The example that I showed in the previous slide was using a quinone molecule, in which upon reduction, it can generate that nucleophilic site, and then this can capture CO2. By reversing this, we can regenerate the organic molecule and also remove that or desorb that CO2 that was captured. So the most of this investigation, they looked at a different variation of quinone-based organic molecules, but there are also other families of organics that can be used. Thiolate and also bipyridine was the other two families that are investigated, but the mechanism would be basically the same. The approach would be the same and the cell configuration would be the same. So we reduce it generate this nucleophilic site in these two cases, which is attractive for this electrophilic carbon center from carbon dioxide. So it can selectively bond with CO2 in order to form this carbamate molecule. And upon reversing these reactions, we can regenerate it, remove that CO2. In order to, for the capacity of adsorption, as I mentioned, this relies based on the prior absorption of CO2 in a solution that can form bicarbonate and proton. For example, when we have potassium carbonate as the absorbent, then sending this stream, the ionized carbon dioxide, into an electrochemical cell in which, upon polarization on the cathode side, the negative electrode, it would attract the positively charged species, including proton. And on the negative side, on the positive side, the anode, it would attract the negatively charged species, which is bicarbonate. So we're basically removing this ionized CO2 species from the solution on the surface of the electrode using adsorption capacitive system. And upon reversing this, washing out the electrode, we can basically remove that bicarbonate, and then down the road, remove that as a gas, CO2 gas. So this is a relatively simple mechanism. It relies based on, again, thermodynamic of CO2 absorption, and then basically the simple capacitive type absorption. But the challenge with this system is the cyclic capacity, because we rely on the adsorption profile, and the adsorption in an electrochemical system most of the time is based on a double layer capacitance, which the overall capacity, which dictates the overall capacity of CO2, is relatively low. So the overall cyclic capacity of this system is relatively low. But there are some other manifestations of this capacitive adsorption in order to design an integrated system in which they can first adsorb it and then down the road mineralize it. So this would be an integrated in situ capture and mineralization process. That was one of the interesting deviation of this capacitive adsorption systems. So that's about the two systems from two families of electrochemical system that can eventually separate CO2 from a gas mixture. The rest of the presentation, I'm going to focus on the system we're developing, the other two families. But before that, I want to talk a little bit about the approach we're taking basically here. The systematic approach to go from fundamental understanding in order to know more about the system and use that to eventually have a system level design and operation to have a successful execution of an electrochemical system for carbon capture. So in this roadmap, the very first question when it comes to designing an electrochemical system for carbon capture is basically, what is the best approach out of that four families, because they have their own advantage and disadvantages. For example, if this, the very fundamental question here is whether this system is applicable for this particular application. For example, one of the main challenges with electrochemical nucleophilic generation is that upon reduction, that nucleophilic site is also attractive for oxygen gas. So that causes some inefficiency, reducing the overall efficiency in terms of removing carbon dioxide, because oxygen can, in this case, compete with carbon dioxide. So if we design a system that has a relatively high concentration of oxygen in the input, such as atmospheric CO2 removal through DAC, then that family of electrochemical approach wouldn't be the best option for us. So we have to take another route in order to design a system for DAC. So that's about the very first question would be what approach and whether the approach is applicable. Then when we know the approach, it would be basically about the formulation. If, for example, now at this point, we want to proceed with, let's say, the pH swing process, then what would be the best chemistry, the configuration, the electrode, and all of those questions that eventually help us to formulate the hypothetical system. Then what we do is normally move towards the modeling part and specifically focusing on chemical evaluation. So now that we have this formulation, that is aiming to remove CO2 from this particular source, what would be the hypothetical chemical parameters within the system throughout the absorption-desorption process? Specifically focusing what would be the CO2 solubility, the selectivity, and vapor pressure, and all of those operational parameters that are important when it comes to having an efficient system. Then, since these are an electrochemical system, we need to also look at the electrochemical evaluation of the system. For example, what would be the operational range for either voltage or current? Because that eventually dictates the energetics of the system. How much energy is required in order to remove 1 mole of CO2, for example. Then moving from modeling, based on the insight from the modeling, we start looking at the experimental, normally starting from the bench scale demonstration, specifically focusing on the key metrics one by one. For example, what would be the efficiency? What would be the key parameters for the optimization? And then down the road, looking at the integrated large scale setup. And the main purpose of that is obviously to have a big picture of the efficiency of the overall CO2 removal process, looking at the long-term performance, degradation, sort of a degradation analysis, and cyclability evaluation. And eventually going towards the implementation for that particular application. So with this in mind, I'm gonna talk about the other 2 families of electrochemical system, and I'm gonna give you 2 examples. In both, we're taking basically this approach. So we're gonna spend 1 slide or 2 on each particular boxes that I mentioned here. So the roadmap would be always the same, and it would be like this. Sometimes we skip some of this because it's either known or it's it's too soon to evaluate, for example, the chemical evaluation when the chemistry itself is new. So first, we're gonna talk about electrochemically mediated amine regeneration, or in short, EMAR. So EMAR is heavily inspired by a conventional thermal processes. So in conventional thermal processes, mainly developed for point source carbon capture, we have an absorber, which relies on amine scrubbing. And then we have a high temperature desorber, in which we desorb CO2 and regenerate the amine and sending it back to the absorber. And in terms of the chemistry, what is happening in the absorber is basically the selective removal of amine by only CO2, forming this complex, amine CO2 complex, this carbamate formation. And this is what comes out from the absorption tower. Then we need to, this would be the selective removal so far. Then we need to apply heat in order to break this bond. And by applying heat, breaking this bond, we can desorb pure stream of CO2, hypothetically, regenerate this amine and sending it back for further absorptions, and then repeat the cycle. So this would be a conventional thermal-based processes using amine for point source carbon capture. When we look at the challenges that are facing these conventional technologies, we see that there are 2 main challenges. One is the high energy requirement of the process, or the energy requirement to capture CO2. And the second one is the high amine degradation, or the high rate of degradation of the absorbent. And when we look at the origin of these 2 processes, these 2 challenges, we see that both of them are because of the high temperature nature of the desorber. So both of them, the degradation is happening in the desorber because of the high temperature, which accelerates the thermal oxidative degradations. And also the high energy requirement is because of the increase, the energy requirement to increase the temperature of the tower. So the idea of EMAR here is basically to replace the high temperature desorber by an electrochemical cell that can be operated at a moderate temperatures. So basically what is happening in an EMAR cycle is that we're taking advantage of the absorber that was developed for the conventional technologies. So basically the absorption step is similar, capture of CO2 selectively, forming this complex. But now in order to break this bond between CO2 and amine, in order to regenerate amine and remove CO2, instead of adding heat, we basically electrochemically oxidize a metal electrode, send that metal ion inside that solution of specifically the anode compartment. And as a result of this introduction, this metal ion would react with amine stronger than amine with CO2, and then form this complex, remove CO2 from that side of the electrochemical cell, which would be the anode. But up to here, we separated CO2, but we still have this amine metal complex that cannot further absorb CO2. So what happens in order to regenerate this absorbent is basically send it to the cathode side, in which we do the opposite reaction that we had on the other electrode. So here we basically electrode deposit this metal center on the surface of an electrode, and then remove that metal from the solution, that we end up having the, hypothetically, the pure amine and sending it back to the absorber. And then we repeat the cycle. So by going towards a high temperature conventional process to an electrochemical cell that can operate at moderate temperatures, we're hoping to address these two concerns related to the conventional technologies. So this is how the EMR system works. And now we want to take that step-by-step approach in order to develop the system. So the very first question is that the formulation, and specifically, what is a good metal and amine combination? So as I mentioned, a good metal and amine is obviously they can complex with each other, because that's the core reaction of desorption. And the second thing is this complexation between metal and amine is stronger than amine with CO2. So this metal complexation is stronger than amine with CO2. So as a result of this, introducing this metal ion, we can eventually remove CO2 from the stream. And also some other factors, for example, the high electrochemical activity and also the stability of metal against, for example, oxidation, because oxygen is also present in most of the flue gas. So after maybe 1.5 or maybe 2 generations of PhD students, we end up selecting this, copper as the metal and 2 amines as the core amine for EMR process. One was EDA and the other one was AEEA. They all satisfy this criteria. And for the rest of the presentation, I'm going to focus on the combination of copper and ethylene diamine as the amine. So basically what is happening is, in terms of the actual electrochemical cell, before sending the stream to the electrochemical cell, we have this absorption process in which we have this ethylene diamine, EDA, in the liquid phase in contact with the gas phase that can selectively absorb CO2, form this carbamate bond, and then send that stream into the anode site when we have the electrooxidation of the metal zero, copper 0 to copper 2+, which can eventually form complex with amine. As a result of that, we have the CO2 released from the anode chamber. On the other side, we have the electrodeposition of this complex, metal amine complex or copper EDA complex, in order to regenerate basically the absorbed amine and sending back to the absorber. So that's how the EMR works, based on copper and ethylene diamine as the amine. So then the next step in our approach was basically looking at the modeling box, but specifically focusing on the chemical evaluation. So both in terms of the absorption step and desorption step, we're dealing with a classic 2-phase gas-liquid contact. And we can apply thermodynamic modeling in order to evaluate eventually the speciation, both in the gas phase and also the liquid phase, by taking into account all the possible species that are possible. And eventually, after developing this thermodynamic model, we need to do this chemical evaluation, specifically looking at CO2 solubility profile or CO2 loading profile at different stages and throughout different stages as well. And also looking at the hypothetical electrochemical energetics that we use this speciation, combine that with the electrochemical evaluation to eventually calculate the energetics. And this model was developed by my colleague, and it was a very good validation between the experimental model and the thermodynamic model, as you see here. So then taking this information from, let's say, the liquid phase speciation, we move towards the electrochemical evaluation. And maybe the key question here would be, now if we want to change the copper concentration on the anode side from this value to this value, because what happens on the anode is the oxidation. So the copper ion concentration is increasing. But then the question was, if we want to increase from, let's say, 0.2 to 0.8, based on the speciation we have and all the fundamental electrochemical reactions we have, specifically the Nernst equation, what would be the profile of voltage for this swing of the concentration of copper? Or specifically, how much potential at each point we need to get to that copper concentration in terms of the oxidation, going from 1 to 2, the anode side. And also the same question for the cathode side. On the cathode side, we have, we need to electrodeposit copper on the surface of copper electrode, going from 2 to 3. Then the same question, what would be the potential profile of this swing of copper concentration? Because we need, that would be the key metric in order to calculate the energetic of the system. So then after having this profile, which is built upon the Nernst equation and also the speciation that we had from the previous slide, then we were able to hypothetically look at the energetics, or the amount of electricity that is needed to remove CO2. So this is what I mean by energetics. So one energetic is basically the minimum energetics, or the area under this curve. So that would be our minimum work to desorb CO2. But since we are using one piece of electrode in each side, we won't be able to set that potential at a certain value. So this graph is telling me, for example, at this point, which represents this part of the electrode, you have to set the potential at this value. At this point, you have to set the potential at, let's say, a more positive value. So, and we know one piece of electrode, we cannot change or dictate the potential at certain stages if they're connected together, because this is a piece of conductor. So we have to set one potential, and that one potential is the one that satisfies all of them. So we have to correct the minimum energy requirement for the system. And we know that if we apply the minimum energy requirement, the driving force specifically on the tip here and here would be very small. The difference between the applied potential and also this curve, the hypothetical curve. So we have to apply an over potential. And since we're using one piece of electrode, then we have this 1 over potential on cathode and 1 over potential for anode. So this would be a more representative of the actual energetic of the system. And by doing that and calculating the values, we were able to compare the energetics of EMAR operated at low pressure and also the high pressure with conventional thermal based processes. And then at this stage in which the process is not optimized yet, the energetic was very comparable to, let's say, the advanced MEA technology that is out there for point source carbon capture. And the other thing is that based on this graph, we know the components of the energetics. For example, this one shows that the minimum work is the major component, or here the minimum work is the major component. So it gives us the ability to basically focus on that particular component in order to eventually reduce the energetic of the system. So using that information, we moved towards the experimental investigation of the system. So focusing on the bench scale demonstration. And in the bench scale demonstration, it doesn't basically represent the whole process. It's focusing on just the electrochemical cell and sometimes one electrode of the electrochemical cell. The advantage is it's a very controlled experiment, so it could give us the evaluation of key metrics. In this example, for example, I'm showing the electron utilization or the electron efficiency in order to remove CO2 and in order to find the upper limit for the process using this chemistry that we developed. And by taking this upper limit, we can basically design the whole integrated process. And this would be the target that we found from this smaller scale demonstration of the cell. So this was just an example of electron utilization, but there are other information that we learned from bench scale that could eventually help us to have a certain goals when we design the integrated process, because the integrated process is very involved, and we have to be very careful when we scale up the system from the electrode size perspective, and also the integration perspective. So moving towards the integrated large scale setup. So the previous case, the bench scale, as I mentioned, is focusing around the electrochemical cell itself, all these reactions that are happening inside the cell. But the whole idea of the integrated large scale setup is basically to have like a continuous process in which the absorption tower is connected to the desorption tower, which happen to be an electrochemical cell. And in order to find the overall evaluation of the system. And to do that, we designed the system in a way that is a continuous automated process. And one thing that I didn't mention here and didn't mention before is that when we have corrosion on one electrode, oxidation on one electrode, at some point we are running out of the anode electrode, where the corrosion happens. So in order to avoid a complete depletion, we have to change the polarity after a certain time. And to do that, from the operational point of view, we have to insert this switch valves and also automate the process. So it also considers that switching of the polarity and also the flow of the electron. So this integrated process, we were obviously interested to study the electrochemical cell. Eventually, what would be, for example, the cell potential or current profile. And also we were interested to also look at the quality and quantity of the gas that was desorbed eventually from this integrated system. And in terms of the scale, this would be a larger scale, more integrated compared to the previous bench scale demonstration. The absorption tower is connected to the electrochemical desorber. So here, again, just an example of one test that we did for 100 hours operation at two different temperatures, at 50-degree temperature and 25-degree temperature, a constant current operation. And the polarity was switched every 2 hours. So this current was between either 0.5 and minus 0.5 every 2 hours. And we were monitoring basically the cell voltage profile, the gas output, and also the fraction of CO2 in that gas output. The very first thing we observed was reversible cycles when switching the polarities, and also no gas production when the current was zero, because between this polarity switch, we turned off the current and what we were flowing the system in order to sort of wash out the system. And at that stage, basically no gas was desorbed. So all the gas was desorbed was driven by an electrochemical current or electrical current, which was coming from an electrochemical reaction. Also, the gas production was very close to the theoretical value. Again, one metric that we study from the bench scale demonstration. And also the IR sensor we had was showing the gas composition of the CO2 composition of the desorbed gas phase was 100% CO2. So no other gases were desorbed. So this shows the efficiency of both the absorption step and also the desorption stages. So this was just an example of how we went from like a more modeling side of EMR, specifically for point source carbon capture, specifically flue gas from power plant. And in order to eventually have a system that is integrated and can work continuously for a relatively long time. So let's switch the gear, focusing quickly on the other method, the other family of electrochemical system that I briefly mentioned on the initial slide of the presentation. And that was basically electrochemical modulation of proton concentration, or sometimes it's referred to as a pH swing process. So the idea in terms of the absorption and desorption, or the idea of CO2 chemistry is pretty simple. We know that in terms of the CO2 speciation is pH sensitive. So that means we can absorb CO2 as bicarbonate and carbonate at higher pH. And we can desorb it when we acidify a solution that was used for capturing CO2. And if we combine this hydration pH sensitivity with a family of electrochemical reactions in which they are proton-couple redox reaction, in which, in addition to that electron, which is necessary for all this electrochemical reaction, we also have this proton involved. So that means by going towards reduction, we can consume proton. And on the oxidation side, we can generate proton. So we can basically make this high, low pH, either local or bulk within an electrolyte that we're exposed to an electrode or a redox reaction. So when we build upon this mechanism for electrochemical carbon capture using proton concentration modulation, this would be a relatively simple mechanism, the chemistry side. But maybe the challenge is the kinetic of the slow kinetic of absorption. As we know, the bicarbonate or potassium carbonate approach for carbon dioxide absorption, the kinetic is relatively small compared to amines. And based on this mechanism, combining electrochemical redox, proton-couple redox reaction with this hydration of CO2, two different families of systems were developed. One is using a soluble redox active species. So the redox is inside the electrolyte. In this case, I'm showing benzohydroquinone. So this quinone doesn't, we don't have a nucleophilic site upon reduction. Rather, we have this proton-couple redox reaction upon the reduction and the reverse on the oxidation, which result in low and high pH, as I mentioned before. The other approach is using bipolar membrane, which relies on water electrolysis in order to eventually generate this high and low pH streams. When we look at this system, there are some challenges still. For example, for this particular system, the solubility is still a concern because the solubility of this organic molecule eventually dictates the cyclic capability of CO2 absorption, desorption. And also the stability is questionable, and also the slow kinetics of this redox reaction. For the bipolar membrane, obviously the cost of bipolar membrane and also other several ion exchange membrane that we use is the main concern. So we revisited actually this proton-couple redox reaction of approach this redox reaction from a different angle. So the conventional proton-couple redox reaction, this redox active species are in the liquid phase, as I showed, for example, for this hydrobenzoquinone. But we thought about having this redox active in the solid phase, specifically on the electrode. So we have an electrode that could host electron and also proton. So after looking at different materials, we figure out transition metal oxide could be a good option, in which specifically looking at the manganese oxide, in which upon reduction, we have this proton hosting, and upon oxidation, we release this proton to the electrolyte. And based on this electrode configuration, we actually designed this process in which on the anode side, we de-intercalate this proton from the matrix of this electrode material. And then the subsequent chemistry is pretty obvious, going from bicarbonate to CO2, and we do opposite on the cathode side. Basically taking the same approach, going from formulation, chemical evaluation, and experimental investigation. But for the sake of time, I'm going to just briefly talk about each step. For the formulation, again, we focus on the absorber in order to know what to expect when this is streamed with a certain concentration of the input CO2 and certain concentration of the absorbent, in this case, potassium carbonate. What would be the speciation when it goes to the anode side, and then focusing on the hypothetical profile of carbon dioxide speciation when we electrochemically introduce proton ions into the solution. So when we introduce proton ion, the pH doesn't change much because of the buffer capacity, but CO2 loading, it's linearly reduced, so which was a good news. So the hypothetical, the desorption efficiency was around 100% when we were introducing proton despite the buffer capacity. Then we take this information in order to evaluate the potential profile, and then the same sort of argument that I mentioned about EMAR, going from minimum, corrected minimum, and the actual operational potential in order to be able to calculate the energetics. And the energetics of the system was very similar to EMAR. And similar to EMAR again, the major part was the electrochemical minimum in terms of the overall energetics. And it was lower than similar capacitive adsorption-based system that was developed for point source carbon capture. Then we moved to bench scale demonstration, basically spending some time on electrode development, going from some initial electrodes using a co-deposition method all the way to optimize electrode using electrode deposition method. Then having this continuous flow process in order to be able to desorb CO2 from an absorption column that a simulated flue gas was fed to the absorption column. So CO2 was removed from a concentration of 15% in the initial gas. Then this would be basically, again, just an example of how to take some of these fundamentals, apply one of these families of electrochemical system, and logistically design a system that could efficiently remove CO2 from a given gas stream. So to go back to these four categories, going towards like the current status of where these electrochemical systems are at, most of the systems are developed at proof of concept stage. And they were developed for both flue gas or point source carbon capture and also air or DAC. And a little bit on the formulation. Some of them, because the formulation, as I mentioned, is relatively simple. So the process formulation, for example, for electrochemical generation of nucleophiles is relatively simple, so not much happening here, but rather they focus on the proof of concept, either on the fundamental or integrated side. So this figure shows like where we are in terms of the maturity of this electrochemical system. And this figure is basically showing the number of publications for the past few years. And we see that a significant increase in the number of publications on electrochemical carbon capture system. And when we look at these categories, we see that they're drawing attention. All of them are drawing attention. And it's pretty exciting to see what happens in the next few years. But what we know is basically we need to provide or adapt expertise that are developed for other CCS technologies. They have been developed, some of them for more than 50 years. So the question would be how we can bring those expertise, for example, those expertise that are developed for point source carbon capture using amine scrubbing in order to take this electrochemical system to the next level, how we can use those expertise to develop electrochemical carbon capture at pilot scale and beyond. The electrochemical carbon capture, I think, is pretty interesting. First, obviously, is because it relies on renewables, but then this system can be connected to the following electrochemical system, which is basically the electrochemical CO2 conversion. So to have like a CCUS or carbon capture utilization and storage scenario. I think if we have this box, the CO2 separation box, an electrochemical system, then the infrastructure, the energy infrastructure for these two systems would be the same. So it's a unique advantage when developing an integrated system. So this would eventually result in a closed loop carbon cycle. And this would be interesting to see also an electrochemical system that are integrated in nature. So that means they can both capture and convert or capture and store and do the storage. One example I showed throughout the lecture, and that was basically the capture and mineralization. So to put the whole presentation into conclusion, we focus on electrochemical carbon capture. It was mainly an introductory presentation. We talked about different families of electrochemical approaches that can be eventually applied for separating CO2 from a gas mixture. That could be from a point source or it could be from atmosphere. And eventually this system could be an additional asset for to play in this blue wedge of the portfolio, which is related to carbon capture and storage. So this is not, let's say, a replacement for amine-based system or membrane system. This is just basically an additional asset for a system that are modular and they rely on renewables. And we significantly actually need to pay attention to this curve because this so far results in a very high concentration of CO2 in the atmosphere. And this didn't happen over centuries. This happens over the past few decades. Actually, when I was born, the concentration of CO2 in the atmosphere was around 350, and now it's more than 410. So we significantly need to pay attention to this. So that's the whole presentation. I was thinking about maybe putting the whole presentation into a conclusion using 4 words. And I was curious what this AI tools could do for me. So I asked ChatGPT to conclude this presentation in 4 words. And I fed ChatGPT with the whole script of this presentation. And what it gave me was electrochemistry transforming carbon capture. I think this is a little bit bold statement, but it was interesting to see that. So it's maybe not transforming, but it's providing an additional asset for the community, for carbon capture community from a different angle. If you're interested to know more about what we do, please visit our website. And if you're interested to collaborate or to be a part of our team, please reach out to us. We also have another profile that promote knowledge on climate change. And that's basically a website that is still at early stage of development. And that's basically climatechange.guide. And I want to appreciate the team. We're relatively a new team at UH. We started last year. And thank you so much also for listening. And I would be happy to answer the questions.
Excellent talk. Thank you, Dr. Rahimi. I want to remind everyone that if you do have a question you would like asked, please post it in the chat, in the Q&A chat, and I will read them out loud. And we already have a couple of questions, so I'm gonna get started with those. First one says, thanks for the helpful graphics. Do all 4 families involve adsorption to either electrode? I am struggling to understand that part about electrochemical separations.
Yeah, that's a very interesting question. So most of the time when we do absorption, let's say EMR, when we oxidize the electrode, introduce copper, because the kinetic is very fast in terms of copper complexation with amine, then we immediately see the CO2 bubbles coming out from the anode chamber. So when the stream is coming out from the anode chamber, we have a 2-phase stream. Most of it is, there's a gas phase, but we also have the liquid phase. To give you a ratio for the large scale setup, we had 7:1. So 7 in terms of the volume was the gas phase, but 1 was the liquid phase. And if you're an electrochemist, you see that this is a problem actually, because the surface of your electrode, which are supposed to be exposed to the liquid phase, is now exposed to the gas phase, which results in higher over potential to drive the same current. So this gas is coming out, this two-phase stream, and then we insert a flash tank. The method we use is normally using a flash tank, and then do this simple gas liquid separation. It doesn't need vacuum. We also in one of our papers, we actually reduced the size of the bubbles by using a surfactant. This resulted in a lower gas to liquid volume, and then a lower increase in over potential when the gas was evolved. In some scenarios, we don't have evolution of the gas phase when we adsorb the species. For example, for capacitive adsorption, we're dealing with the ion. So we first convert in the absorption tower, convert CO2 to this bicarbonate, then remove this bicarbonate on the surface of the electrode. So we're basically removing the ionized species of CO2. But most of them, we're evolving gas. A good technique from an electrochemical point of view is to design a gas diffusion electrode. So once you evolve the gas will be removed through a gas diffusion electrode by, let's say, a sweep gas or a vacuum. So it won't accumulate in order to have a big chunk of gas space in the liquid section.
Okay, awesome.
Yeah.
Next question. On slide 22, is the electrode active material coated on fibers? What is the advantage of this structure?
Excellent. Yeah, manganese oxide is actually coated on different surfaces of carbon cloth, carbon felt, and carbon paper, which are different in terms of the porous structure, and also different eventually in terms of the stability of this layer that we are forming on the substrate. The advantage is obviously improving the conductivity, because sometimes when we develop this metal oxide, we combine it with, let's say, carbon black throughout the fabrication process, and we put it on the surface of a conductive material, in order to eventually reduce the charge transfer resistance, which impacts significantly the over potential needed to drive the current. So one reason is basically improving the conductivity. And the second reason is obviously these are porous structure. So that means it provides more surface area per projected surface area of the electrode, which is a very advantageous aspect. So the overall size of the electrochemical cells is smaller compared to when we electrode deposit this manganese oxide, let's say, on a flat surface.
Okay, awesome.
Yeah.
I think we have time for one more question. Is ocean capture a viable option? If it is, will the salts present in water cause any issues? Sorry.
That's a very good question, because looking at the slide that you have in front of you, I have this part empty. But I'm guessing next time I'm presenting this, it would be all about carbon capture from ocean. The major part of our group right now is focused on carbon, not the major part, like at least 25 to 50% of our group is working on carbon capture from ocean, because it was unpublished result. I couldn't include it here. But it's a different dynamic when it goes to ocean. We don't have the flexibility to select the electrolyte. The electrolyte is dictated. So that means, as he or she asked, we have tons of salt that could interfere with the system. So if it goes back to that first question, the applicability. If we want to select, let's say, an EMAR process, obviously this doesn't work, because it's so risky to deal with an amine process, sending it to the seawater and then sending it back to the ocean. So that would be out of question. Then when it goes to something like capacity of absorption, the electrolyte is just looking at the charge. So ideally, we need to remove bicarbonate, but there are tons of other anions in the ocean that could be absorbed on the surface of the electrode. It's if this electrode is not selective towards one ion. And considering the bicarbonate concentration in the ocean compared to sulfate and chloride, we would definitely have this chloride or sulfate removal, which doesn't do a job, which reduce the efficiency of the process. So in that case, we have to be very careful with designing the system. So that applicability, the very first box that I showed, when it comes to ocean capture, it's very tricky. A long story short, almost all the technologies that are developed for ocean capture so far, which is relatively new, all rely on one family, and that's basically the pH swing, because they rely on the aqueous phase. It doesn't necessarily involve introducing a secondary redox active molecule like quinone. It could rely only on water. So that's a pretty tricky question. Hopefully next time I'm presenting this, we all talk about ocean capture.
Okay, awesome. Maybe just, okay, we have one more question. So maybe just a quick answer for this one. Besides quinone, are there any other chemicals that we can use for the electrochemical CO2 capture?
So it depends on whether we want to go for a generation of nucleophiles. If that's the case, we have this thiolate and bipyridine. If we want to use quinone as a redox active that could do proton-copper redox reaction, Then most of the investigation that I looked at in the aqueous phase is quinone, but I don't see a reason not to use other molecules as long as it's a proton copper redox reaction. The quinone chemistry / electrochemistry is relatively known. That's why people use this quinone, and the structural tunability is just amazing.
Okay, great. Once again, I'd like to thank Dr. Rahimi for an amazing talk. And I'd like to thank all of you for joining us today, and have a great week.
Thank you so much for having me.
Awesome.